Okay. Thank you very much, Guilherme, for the introduction, and thank you all for coming. It's really a pleasure to talk about a little bit of science, but mostly a little bit about the history of the laser and plasma group, which is intertwined with the history of the department. So it's always nice to reflect a little bit how we got here and what we plan to do as we move forward. So I'm going to tell you, so in the next, let's say, 45 to 50 minutes, I aim to guide you a little bit through a little bit of the history of plasma physics, to give you some pointers of how we got here, also to discuss a little bit how we see things as we go forward. So this is kind of my plan for today. I have too many slides, so at some point I will start to rush up a little bit, but so bear with me, okay? So so the purpose is really to celebrate the 30 years of GoLP. That I'm now the scientific coordinator, but this is a long story, a 30-year long story. So I will try to guide you through this, and I would like to also thank, a big thank you. Let's see if this moves forward. Oops. If it doesn't, oops. I have a technical problem here. Oops. Trying to move this. Oh, okay. Let's see if now it. So a big thank you to everyone that has contributed with material, slides, and feedback to this presentation. Of course, everyone that has been part of GoLP for the past 30 years. So on my plan, I have this talk divided in three parts. First, a little bit, I will tell you a little bit about the early history of lasers and plasmas at IST. Then I'll tell you a little bit about GoLP, and I will share with you a little bit about our vision, or the vision of people here at GoLP, of what we expect for the next 20 years. So this is kind of the plan for today. People that have taken classes with me, they know that I always recommend that you listen to a talk that is called How to Speak. He's a professor from MIT, and one of these advices is that you should use a prop, okay, in your talks, okay? And my prop is the first laser at Técnico, which is the first laser in Portugal. And that my kind friend, João Mendanha Dias, he makes me wear these things. Allows me to, okay, let's see if I can do this. Allows me to show you the first laser at Técnico, which is this one. This is a flash tube, and inside the flash tube there is a crystal, which is here, which is a ruby crystal, and this is what makes up a laser. If you look at it, well, there's a nice picture here in the center. This is the first laser by Theodore Maiman, 1960. So at Técnico, in the mid to late 60s, we already had this system here to do experiments. And the person that pioneered this at Técnico was the first president of the physics department, Professor Alves Marques. Many of you know about him, which was the first PhD graduate of IST. He was supervised by António da Silveira, which some of you have heard of, and some of you here had classes with him, so can tell you very, very peculiar stories about António da Silveira, but this we can discuss over coffee. So this is important just to tell you that right from the start, right from the following the invention of the laser, we already doing experiments, mostly molecular and atomic physics experiments, but we already had this tradition at IST. The plasmas, they come a little bit later, okay? And there's a nice paper by a researcher here, Professor José Cabral, and he wrote a paper for Gazeta de Física, and this is very well documented, nice paper, and he explains how plasma physics started in Portugal. So there was a very famous professor that will show up a little bit in front, called Abreu Faro. Some of you probably already had sessions in the Abreu Faro amphitheater, and Abreu Faro was kind of the president of GNICT, of the equivalent of GNICT at the time, and decided that it was very important to send people to do PhD abroad. And so he sent abroad a number of people here. Some of you will recognize the names. Rocha Trindade, Namorado Rosa, Matos Ferreira, he was the president of IST. Costa Cabral, he's the author, outstanding experimentalist, fundamental plasma physics and then nuclear fusion. Armando Brinca, plasma astrophysics, António Costa, Tito Mendonça, and non-linear waves in plasmas, Filipe Romeiros. So this was what was kind of interesting, is that this comes, all these people, they have graduated abroad, and about almost of all of them, I'm not sure, except for Namorado Rosa, they came back to IST right in the mid-70s, late 70s. So this brought in together people that were trained in the best universities in the world. Just look at the names. So it's just amazing. And these people came back to IST. They founded plasma physics at IST. Plasma physics itself is a relatively recent discipline. So the first non-military and open research started around 1958. So we were really at the forefront when all these scientists came back to Portugal to do their research. The first plasma physics paper in Portugal is a paper by 1975, is a space plasma physics paper from Armando Brinca. So this is the person that graduated in Stanford University. He was actually doing already simulations, then he becomes kind of a guru of particle in cell simulations, which is also something that we do at GoLP. And what is interesting is that he was the first president of the electrical engineering department, which shows there is always a nice connection between physics and electrical engineering. The first laser plasma paper in Portugal came up a few years later, and it's not surprising that this involved Professor Tito Mendonça and Professor Armando Brinca. One is an expert on was already an expert on the kinetics of plasmas, and Professor Tito Mendonça had graduated in Orsay, did his thesis on nuclear fusion, but with a focus on how to heat up and how electromagnetic waves interact with plasmas. So it was natural that they came together and did this paper. And actually the first PRL in laser plasma physics in Portugal was published in 1979. And this is particularly singular because from 1970 to 1979 in Portugal there were published 3 papers in PRL. Okay, which is we are in a different world today. Okay, this was the second or the third paper in PRL on that period. So this was very exciting, but there were other exciting developments before GoLP was founded. One of the founding papers associated with the way that plasmas heat up was published by Professor Tito Mendonça, and he studied a phenomena which is the chaotic dynamics of electrons when you have 2 electromagnetic waves interacting. And this is one of the founding papers on the way that electromagnetic waves heat up plasmas, and in particular how very strong electromagnetic waves interact with an electron ion plasma. But there are 2 additional papers that I would like to tell you about. The first one is beat wave excitation of plasma waves, and this is in connection with a very famous paper, from a famous plasma physicist called Martian Rosenbluth. And there is a small non-linear correction on some calculations associated with this particular problem. And Professor Tito Mendonça was one of the persons that was involved in the debate if this shift was positive and negative. Okay. This issue was then solved in a PhD thesis by someone that I will mention a little bit further on, called Warren Murray, and actually found out that the shift was the opposite sign of what Professor Tito Mendonça predicted here. Okay, but this is how science works. Okay, we always develop our work on the shoulder of giants, and what is interesting is that Tito Mendonça, he met Ricardo Galvão, is the person that is going to get an honoris causa in early December. They met at ICTP, and they worked also on this problem, but in connection with fusion. So there was a natural connection here between all these people. And one of the problems that if you look at the PRL in detail, and if you look at other papers that Professor Tito Mendonça was working on at the time, he was always interested in understanding how an electromagnetic wave propagates through a plasma and modifies its properties, making it nonlinear. And so he has another paper with this person that I just mentioned, Abreu Faro, about what happens when you send in an electromagnetic wave through a stationary gas and you modify the properties of this gas. And you have a transition between a gas and a nonlinear medium that is moving at the speed of light. And I'm mentioning this because one of the landmark experimental results is essentially connected with these ideas that Tito Mendonça was exploring. So this is kind of all the trajectory that we had up to this point. Professor Tito Mendonça, he founded the nuclear fusion activities here in Portugal. So he was the first PhD in this area in Portugal. So he founded the Nuclear Fusion Center. But then things evolve, and those that know Professor Tito Mendonça know that he's a very restless personality. So he's always trying to do new stuff. So in 1993, he founded GoLP, okay? And he founded GoLP with another professor here in the department. His name is David Rezendes, and with a bunch of students from the left that at that point had just started. And so GoLP was founded in 1993. We were in the Electrodynamics Center from 93 to 99. Then there was a reorganization. We became the Centro de Física dos Plasmas for 9 years approximately, and then we are at IPFM. I'd like to stress this connection with the students, because this is what I think is one of the hallmarks and one of the distinctive ways of how GoLP approaches science is through the connection with the students. And I think this is best exemplified with these two examples. So we used to put these things all over Técnico. And if you realize, this is our internship program from 2001, and it's already stated here, this is the third edition of the program. So more than 20 years that the students and interaction with the students is absolutely critical to what we do. And this connection with not only with students but with the general society has also been a hallmark, and this is an example of what we've been doing for many years, also inspired by some of the activities in nuclear fusion, working not only with the students here at IST but also with high school teachers. And this is, I think, it has been transformative in the way. This is Gonçalo. He's probably well, he was younger than today, but this is not surprising, right? But in a visit to the Rutherford Appleton lab with some of the people involved here, we can pinpoint exactly our starting day, because Professor João Mendanha Dias is an experimentalist, so he likes logbooks. Okay. So he has his logbook. It's stated here, 25 January 1993. And this is the meeting of the optics group. So Tito Mendonça is there. Then there is David Rezendes. Then there's Pedro Conceição, who is now the Director General for Development of the United Nations. Then there is Luís Lapão. He's now a professor in management sciences connected with health. There's João, Engenheiro Mendanha Dias. So we were proud graduates from IST, so everyone was engineer. Rui Guerra, he was not an engineer because he was coming from some other place, so he was not engineer. And then I'm there, I'm giving this theoretical support. Okay, so that's kind of funny. What was cool at the time, this is what happens when you're building stuff, okay? So you do very crazy stuff. So fortunately, I'm the one giving the presentation, so I could pick up the pictures, okay? But you could see the attitude from these scientists. Okay, some of them are just helping with the brooming, right? Like myself here, and you can feel the love there between two of the researchers. Okay, so these are. I think this has been kind of a tradition in the group to take things in a light way, okay, with some sense of humor, and so we had many students going through, and what is amazing is that we had more than 40 PhDs in the last 30 years. And this is all the people that have graduated from 1997 to 2022, which I think is quite exciting. They marked in black first generation PhD students, so students of the Villerezendes or Tito Mendonça. In blue, the students of the first generation, and we are already going on the third generation, which is very cool. Okay. What is interesting, and this is also a hallmark of GoLP, is that we are a mixture between experimental physics and theory and simulation. So I marked in black the ones that the theses that are experimental theses, and in blue the theory and simulation. And you see that there is a nice balance between these. So these are these descendants. So where are we coming from? So we are students of Tito Mendonça, most of us, and Tito Mendonça was a student of Delcroix. So he's a scientific brother of Professor Matos Ferreira, which was also a student of Delcroix. And Delcroix is the father of plasma physics in France. Then you can go up here, Yves Rocard. He was the father of the French H-bomb, Fabry, from the Fabry-Perot. Then you go up here and you have Louis Pasteur, and you can go up and you have D'Alembert and all these guys. So this was quite fun to know where we're coming from. So the plasma physics now at what happened in the electrodynamics center is that we have the group N prime, where Vasco and Luís Alves and other people work, which are descendants of Matos Ferreira, and we have GoLP, we are the descendants of Tito Mendonça, and we all come from Orsay, okay, from Delcroix. So we are cousins, right, scientific cousins. Okay, so the first, of course, the first works that were truly associated in the first projects were really more theoretical projects. And I would like to highlight here three people that have been of paramount importance for us. One is Leonard Stenflo, he's from Umeå University. He was Secretary General of the Nobel Committee and all that, so he was the person that would write the letter on the typewriter. So one of our colleagues had the opportunity to see the typewriter where they actually typed the Nobel Prize letters. Padma Shukla, a very prolific theoretician in plasma physics, and Bob Bingham. And Bob Bingham is a person that has been critical in all our developments because he kind of opened our network to a much wider network. And the first important connection is through the Rutherford Appleton lab. So this lab is one of the major laser labs in the world. And right from the start, we had the opportunity to start to do experiments there. I think we see here Ricardo Fonseca doing experiments, which is surprising for those that know him today, right? And Madalena graduated with us, and Gonçalo still looks like an experimentalist still these days. So this was kind of important because it was natural to keep doing theory, but the vision of Tito Mendonça and the Villerezendes is actually to do both theory and experiments, and this takes some time to build up. So most of what we did was actually grounded on this close collaboration with the Rutherford lab, and I will show you in other directions. So the first experimental paper was published in 1996. So this was a paper for the master thesis of João. This was for a nuclear fusion diagnostic using CO2 lasers, and this is the first experimental result coming out of the of the laboratory for intense lasers. And the laboratory for intense lasers was really a transformative step here, because it really brought us into the world of high power and high intensity lasers. You can see here how everything started. So this lab is on the -2 level. I think it's not on this building, it's on the next building. So construction started in 1997. 1998, we already had a big chamber there. 2002, it's already quite filled up. This is 2012, and now there's a new laser system that lives along the original laser systems that have been built. This has been transformative for us and for research with lasers and for the group, because of there are essentially two reasons here. The first is that due to the fact that we had this lab here, we got involved in Laser Lab Europe, which is this network of the top laser labs in the world. So this opened up a tremendous amount of opportunities to do research. And from a national standpoint, this infrastructure was recognized as one of the most important infrastructures in Portugal. But before this, the experimental work, we had through the equivalent of Laser Lab Europe, we had access to other labs in the world, and we did an experiment at the LOA. And this experiment was really the first step for visibility from the experimental side from GoLP. And on this experiment, we send in a laser through a gas. Remember this paper from Abreu Faro? Okay, we send a laser through a gas. There's a change in the index of refraction. And now, if you co-propagate a laser light through this transition, or if you counter-propagate laser light through this transition, it's possible to demonstrate that the frequency shift of the co-propagating or the counter-propagating light will be different. And you can actually infer the velocity of propagation of this transition by comparing these different shifts. And this is what is illustrated here. This is the spectrum, okay? Frequency going up. So this is the original laser light. This is what happens when it counter-propagates with the ionization front. This is when it rides the ionization front, when it co-propagates with the ionization front. So this was kind of our first landmark experimental papers, was published in Physical Review Letters. I don't know exactly the statistics, but there were about 5 Physical Review Letters every year. So this was still significant in this experimental result. Okay, so this was kind of the result that could make the news, right? So you can see the line. A boleia dos fotões, a aceleração dos fotões. I mean, this is just amazing. And what's written here, it's even more amazing. Portuguese is accelerate photons, photon acceleration. Yeah, so this was really cool. And we even had a party. I don't know if you recognize this. This is the Bardo complex. Okay, we are having wine, but the news says that we are having champagne. Okay, so this was just after the 85th birthday of, this was 24th May 1997. So this was right after the 85th birthday of Técnico. So there was also all this celebration. This is also something that we try to do right from the start. Is whenever we have something that is exciting, we try to share it with as many people as possible. And so this is something that we learn how to do, is to put out the news. And you can see Professor Tito Mendonça enjoying his wine with João. But at the time, I don't think João was yet a wine expert as he is today. So this was one of the landmark results. The other exciting project is something that we have been pursuing for many years at GoLP, is this connection between what we do in companies. And so we had a very cool project, which was a LiDAR project, or I like to call it lasers on a van and on the road. And so our colleague José António Rodrigues really set up a laser that you can see the telescope here, put it inside a van. The van even had the logo of IST, and then you would shoot the laser, okay? Well, in different places, okay? We were shooting it outside of IST. I mean, this was really dangerous at the time, but okay, but you are not, and you can imagine with the airport, it's just crazy. We were doing other things with lasers at the time. Okay, and so this is an example. So this is a neodymium YAG laser, but it's frequency double, so it's green, and so you can see the light here. And now what this system has is a telescope that collects the backscattered light, and so this is a pulse. So if you measure the time that your photons take to be backscattered, you can infer the properties of the medium that you're probing. Okay. So this was quite exciting. This was funded initially from the electrical company, from EDP. It was funding this. Then there are other European projects. We were also discovering many other things as we were going along, and we didn't even know, but the newspapers were telling us very exciting things. Okay, so for instance, for a paper published in Nature, they were calling it efeito da palhinha, which is still a running joke with some of the person. So Marta, when she published the paper in Nature, she also emits for the first time X-ray lasers. So Marta, and it was really amazing because the discovery itself was emitting an even amazing laser. Okay, so this was very exciting times that just show. I mean, science communication has evolved a lot, but at the time things didn't make any sense. Okay, so Marta was probably the first person that ever emitted an X-ray laser. Okay. Okay, a transformative component of our work here was due to our interaction with UCLA, and Ricardo Fonseca was a PhD student there. And he brought us into the interaction with this team at UCLA that is very well known for doing numerical simulations. So the father of numerical simulations in plasmas was a professor there for many years, and at that point Ricardo Fonseca was a PhD student there, and he brought this code Osiris to IST, and this kind of started a new branch for our development. We were quite excited at the time to be back in Lisbon, and more exciting to build machines. And this is just some of the examples. At the time, this was coined as the fast Mac cluster in the world. Okay, there were not that many, probably there were about 3. But this kind of shows us, this picture just to show the boxes that we proudly stacked in the hall. But this was the first cluster that we had there. It was very similar to the one that was at UCLA. Then we built a second one. This looks a little bit more professional. And then we had a IST. This was a node of the national network for this was an IBM machine, and this is the cluster that we have these days. So along this, we've been not only developing numerical simulations, but bringing the infrastructure to do these simulations. And with this, we were able to do some landmark work equivalent to what we did with the experiments. So the first that I would like to show is the first multidimensional simulations where you connect plasma physics with astrophysics, were probably some of these that are shown here. This is an example of a simulation done in 1999 on a Cray MP machine in the US. And I still dare my students to beat what Ricardo did here, okay? This is just a kind of a standard instability where you have 2 plasmas streaming through each other, you generate some magnetic fields, and you have these field lines. You can see this was 1999, which is pretty impressive because the Cray was probably less powerful than any cell phone that we have here. We only published this result because some collaborator that we knew from Berkeley at the time said, okay, this is very relevant because we were using this as a benchmark for Osiris. So we didn't even care too much about this result. This instability that I'm showing here is at the heart of the formation of shock waves. And this is one of the first simulations of these relativistic shock waves that occur in plasmas, where we take into account electrons and ions. And you see these filaments share the same physics as what's happening here. One of the directions that we also pursued is this laser wake field acceleration. I've showed this movie many times because it really highlights the physics. We send in a laser through a gas or through a plasma. It pushes the electrons out. It forms a bubble. This bubble is nonlinear. Some of the electrons fall into this bubble. They are accelerated. They oscillate transversely. And since they are relativistic and they have a transverse acceleration, they radiate X-rays. And so this captures all that physics. If we can accelerate electrons, we can accelerate protons. So we started to look into proton acceleration and look at how lasers very intense lasers can be used. And as a result of some of our work in collaboration with the experimental team at UCLA, kind of landed, Frederico Fiuza landed this discovery of Nature Physics in 2012. Also following, most of the lasers that people have been exploring are relatively straightforward lasers up to a few years ago. So everything is Gaussian and perfect. But you can actually play with the structure of the lasers, can manipulate the polarization, can give it higher order modes. And following work that was pioneered here again by Tito Mendonça, we've been exploring the interaction of light with matter with more exotic properties. And exotic properties are very funny polarizations, very funny higher order moments of higher order modes of the laser system. And this is just one example of how you can play with the laser light and actually what kind of structures they can leave behind. So the topology of light can actually influence the topology of the plasma that is left behind. One of the challenges that these days in our field of research is to understand what happens when you push the intensity into regimes where quantum electrodynamics starts to be important. And so one of the most exciting developments that we had here was actually the study of the fundamental processes when you collide a laser with an electron beam, and quantum electrodynamics is important, or when you collide two lasers and you just have a seed, okay? And the interaction is so strong, the field is so strong that you generate a cascade that is driven purely by quantum electrodynamics processes, even though the lasers are classical. So this is really a birth of a new era for high intensity lasers, and we are right there at the start. And in recent years, we've been exploring the connection of these fundamental problems to understand more exotic objects like neutron stars. And so these days, it's possible, many groups are doing it, and here at GoLP we are also doing it. It's possible to do global simulations of neutron stars, or look into the details, what is happening in the equatorial plane or in the polar cap. And the physics is extremely rich, and what is exciting is that the tools, the numerical tools, and the theoretical tools that we use to understand what happens in lasers is also the ones that we can use to understand this phenomenon. So this has been very, very exciting, and of course not only from the theory side, but also from the experimental side, we've been right there at the front. And I really like this slide because this is Marta's team at LCLS on one of the first experiments that was done at SLAC about 10 years ago. So if you've heard, LCLS is the first free electron laser, X-ray free electron laser. And so we had one of the first experiments there, led by Marta in one of these MEC stations where they generate harmonics to probe, to couple this with the X-rays from the FEL. The team, Marta's team, has brought many of the physics that they are exploring in connection to high harmonic generation and these X-ray sources has been brought to to IST, and we have a number of problems, a number of projects led by Marta here, on funded by the European Innovation Council or equivalent funding agencies that have really allowed us to bring in an extra facility besides the laboratory for intense lasers. We have also now a facility that is changing names, right, Marta? Now it was Voxel and NanoXcan, and probably it will change names soon. Okay. So now it's time to talk a little bit about the future. So I tell you what we have done up to now. So we've covered the story of a little bit of the story of plasma physics, a little bit of what we have achieved in the past 30 years. Of course, this is a very I hope it's not too biased, but of course, but it's always there's always a selection here. So bear with me if you don't see your face or your slides here. There are many more exciting things going on. It's nowadays this is a large group, about 40 people, so there's always exciting stuff and stuff happening. So to understand a little bit what we expect for the next 20 years, I asked a number of people in the group, okay, what do you expect that someone that comes here in 20 years for the 50-year celebration, hopefully we won't see a change on the center, right? Because we have the Center of Electrodynamics, we have the Center of Plasma Physics, IPFN. So hopefully we'll be here with IPFN. So what should we expect for the next 20 years? I'm not going to be the one for sure going to be here on 20 years, but someone will be here in 20 years time. And so I asked some of the people to tell us a little bit what should they expect for the next 20 years. So in terms of laser research, there's what I think is important is that Europe is really leading the effort in lasers and laser technology, and the high intensity lasers. Europe is leading is the powerhouse for these type of infrastructures. Europe has also made a tremendous effort. So the highest intensity lasers, they are on a few facilities. So one needs to understand how universities, how smaller facilities work on this landscape. Also, and what is also highlighted here, there is an increased interest on fusion, laser fusion, due to the results at the National Ignition Facility. So definitely there are going to be very exciting times on the big infrastructures, and there's a role to be played by the smaller infrastructures. And so clearly there's the original mission that we should pursue, which is the education and training of young researchers, and then use our facilities as stepping stones for the larger systems. And the experimental teams here have been very successful in pursuing this strategy. What is also exciting is that with the expertise that we have these days and with the different sources, there's the opportunity now to connect with other areas. So we have X-rays, we have terahertz sources, so there's connections, possible terahertz sources. We have radiation at 1 micron, we have radiation at 3 microns. So there's the opportunity to connect with other areas. So definitely future directions are exploring the connections of lasers with all these important programs. So there's many links with other communities that need to be explored. And in Spain, there's also a big laser in Salamanca. There's also a vibrant community, so there's definitely room for interactions with the Spanish community. A recent addition to the portfolio of labs at GoLP is a ultra-cold atoms lab. And this is of course, a very fundamental research-focused lab. But what is exciting is that there are a number of possible applications in the future associated with quantum technologies, atomic clocks, and microgravitometers that have a broad range of opportunities for applications. In terms of plasma-based accelerators and laser plasma accelerators, we have both expertise experimental expertise and theoretical and simulation expertise. So this is an area where you can, can continue to have an impact in experiments, high performance computing, and theory. So there are several overarching goals. The big overarching goal is to keep reducing the size of our accelerators, to make it smaller and smaller, and to push the beam properties to the level that you see on conventional machines. This is extremely hard, and for some cases it might not even be possible, but that's why we do it. It's because it's hard. But on this pursuit, there's many connections with medicine, technology, and fundamental science that can be explored. So there's the one stream where we aim to develop in-house experiments, and then the other stream is to take this expertise and bring it to large international problems. One flagship example is the ability that was pioneered by a team of Imperial College with people here, our colleague Nelson Lopes, to use X-rays to do unprecedented images of biological samples. So this is a tomography of a mouse embryo, just to show what is the level of resolution that these sources, X-rays generated from a laser plasma accelerator, can really push forward. So this is definitely an area where we want to invest, is to understand how can we optimize these sources. The other, of course, is to understand a little bit better radiation. On this process, we have tremendous sources of secondary particles. They can be either electrons, ions, but also X-rays, gamma rays. So understanding radiation is absolutely critical. And even from a more fundamental perspective, using the more exotic properties of light. For instance, one example here is self-bending of light. So playing with these beams with exotic properties, the beams can actually turn in free space and make these funny trajectories. So there's definitely a new frontier, which is the combination of the ability to produce these lasers, like some faculty members here at Técnico are already pursuing, with the interaction of these beams with matter. In terms of the connection with high energy physics, which is has been an important goal, we've been developing a large plasma source here that is now installed at CERN as part of the AWAKE experiment. And you can see here, you probably have never seen the CERN tunnel lighted with such flare, and in different colors, because these are different gases. Okay, so some of argon, helium, and xenon. So you get a CERN tunnel lighted in different ways, and this has been used as a stage for a plasma-based accelerator. And as in all projects involving CERN, we are talking about very long time scales, where we are at the stage where we are developing length scalable plasma sources that are going to be staged in between 2025 and 2030, and then if this is successful, then we'll try to do experiments with these electron beams. On the high intensity frontier, there are a few directions that are exciting. Some are associated with exploring the fine properties of quantum electrodynamics using the collision of lasers and electron beams. So this is one of the most exciting frontiers these days. So in the next few years, many experiments are going to be developed, exploring the QED cascades, not with the lasers that people are building right now, but with the lasers that are going to be the next generation of lasers, like 25 petawatt laser systems that are now being planned, and explore this connection between quantum electrodynamics and general relativity in these objects where plasma physics does play a role. So the magnetospheric properties do play a role on the radiation that we see coming at us. one of the possibilities. So we are always looking for bigger and bigger machines. I didn't point this out clearly, but a fundamental component of our work is to use not the small clusters that we have here, but okay, we also use those, but using the biggest machines in the world. So we are always looking for opportunities to explore and platforms to explore our algorithms. So one of the possible directions is quantum computing, and this is definitely an exciting direction. Understanding if quantum computing can actually bring some computational gains to what we do. As I've discussed, there's an exciting frontier and an exciting opportunity when we are able to manipulate the properties of light, understanding how these properties, how this light interacts with matter is absolutely an open field. And so answering experimentally what kind of shape can we give to these electromagnetic pulses, what kind of modes, and how do we interact, how these modes interact with the matter, and in particular with plasmas, is definitely one of the most exciting frontiers when we are looking at light manipulation across a wide range of frequencies. This is the more fundamental aspect, but when we start to have all these sources of radiation, I've spoken about X-rays, gamma rays, and we can also generate terahertz and all that. And the ability and the combination of this ability to detect photons at these different frequency ranges and to do images, there's a broad range of opportunities that is opening up. And so one question that definitely needs to be answered is what innovations will this bring? When we combine all these, the opportunities to have single photon detection with data acquisition and high rep rate sources that these lasers can deliver. Also, in terms of applications, there's there's a holy grail that needs to be pushed forward, which is Moore's law. We need to keep pushing our transistors, the density of our transistors. This means that we need to be writing transistors with lower and lower wavelengths. So we need to push our ability to generate sources that can write our wafers with lower and lower wavelengths. And so one of the questions is, can we actually develop these sources of radiation in extreme UV and then on the X-rays that will allow us to continue to push the way that we write and that we produce these chips. So this is definitely one of an obvious direction when you start to be able to manipulate light across these many frequencies. Of course, we still need to continue to look up to the sky, and there are many opportunities here in the lab to understand what's happening in the sky with this combination between astrophysics, big lasers, and numerical simulations. So there are a number of questions that we'll be able for sure to address in the next 20 years. Understand how magnetic fields are amplified by cosmic rays, how shocks accelerate particles, and what are the fundamental properties of these relativistic shocks. So there's a wealth of there's a convergence of big lasers, astrophysics, and numerical simulation that is really opening a tremendous window into some of the big problems in astrophysics and plasma physics. And I think I'm within time, okay, which is rule number 0 of a talk. So I'd just like to kind of our motto at GoLP is committed to continuously raising the bar. So this is what we hope to do for the next 20 years. And I really look forward to attend in 20 years, sitting there, of course, the excitement that the next 20 years will be. This is it.